Hello everyone, thank you for joining AWS Modern Application Workshop and welcome to this session. So today we're going to talk about three things and we have a couple of labs that designed to help you understanding on architecting event-driven with AWS. So we are really excited to be here and sharing with you regarding event-driven architecture and how to implement with AWS. So for today, we will talk about the concept and implementation of event-driven architectures. And we think this is really important because we've seen that more customers are adopting the event-driven architecture. And the thing about event-driven architecture, the most important part is the implication. Event-driven architecture makes their team so much more agile and so much easier to build scalable, reliable, and resilient system. And also about this workshop is actually tailored for intermediate developers. And we might skip one or few basic things as we assume that you have certain experience building on AWS, so you already knew a few basic concepts. But don't worry, if you have any questions, our technical experts teams are standing by. So three things that we are going to cover for today are microservices, asynchronous communications, and lastly orchestration. So the thing about microservices is it's challenging. It's challenging because it's a distributed system. And when it comes to distributed system, the thing that we need to understand properly is how we design the services to interact or communicate with each other. And that's exactly what we're going to discuss. As I'll be your host for today, let me introduce myself. My name is Doni Prakoso. I'm a senior developer advocate at AWS, and just like you, I'm a developer as well. I have started my professional experience as a software engineer, R&D manager, and CTO for several startups. I'm so grateful for the companies that I've worked with in the past were strong advocates of modern technology in various verticals, from banking industry, telco, to startups. I specialize in microservices and event-driven architecture, and that includes serverless and containers. So if you have any questions about microservices, feel free to drop me a message on LinkedIn and Twitter. So this is a series of things that will be our topic of conversation. And hopefully this agenda gives you a big picture on what we're going to do in the next 2 hours. First, we will do the requirements checking. Since we are going to be using the CLI and a lot of coding, I hope that you have all the tools required in this session, and it will make it easier for you to run this workshop. In addition, the concept of this workshop will alternate between slides and labs. We will look back at why microservices are increasingly becoming the choice for developers. Then we will try to discuss why a building synchronous API like the REST API is not sufficient for building microservices. Now from there, we will start discussing the design patterns that are commonly used in modern development for API. Now that we understand the constraint as well as the basic concept for asynchronous application, we will try to re-architecture a REST-based microservices to become a microservices with asynchronous communication. So we'll see how you can use choreography as well as orchestration as two commonly used concepts. And after that, we will close this workshop and see what you can improve after understanding the concept of asynchronous and event-driven architecture. Sounds good? Let's get started. Now these are the objectives we hope you will get after this workshop. First, you will understand synchronous and asynchronous implementation in microservices. Now, the second, how to design interactions between services with orchestration and choreography. And the last objective is you will understand on how to use AWS CDK for modeling resources and also make it easier to deploy and also cleaning up. Now, these are the three key takeaways and these are the foundation for which we build this content. Okay, to start this workshop, we will do a requirement checking and we will wait for 10 minutes just to make sure you all have the tools and source code that you need. First, you need to do a git clone for the source code link and it is shown in the image. And after you have successfully cloned it, you will get the source code. In the source code, there's a bash file, which can help you to check if you have all the requirements needed. If anything is missing, the tool will provide the URL info you need to perform the installation. So if you have any issues, please post your questions in the room. Our team and myself will be there to help you out. So let's start now. I will close my webcam and come back when 10 minutes are up. Okay, so I hope everything is set and we can move on. So let me iterate why people are moving to microservices. Most of us started with Monolith, and most common reason why we choose Monolith is because it's relatively easy to build. And there's definitely nothing wrong with that. However, the more our business grow, we have more users, we add new features, the more complex our system become. It's inevitable. And one of the solutions to handle this kind of challenge is to build a distributed system, such as microservices. So monoliths are easy to build and reason about. It's way simpler to understand how the system is going to work when all of your data is in one ACID compliant database and all of the calls you're making are operating against the same environment. And it's also easier in terms of development as all of team members are contributing in a single code base. But since we only have a single repo, problem that usually rising is if we have multiple teams, it's becoming the bottleneck on release pipeline. Now the reason is because having one large code base, it makes a tight coupling where everyone are working on have a high probability that it might affect them. Among all the technical and managerial reasons, the main problem is monoliths don't scale, and we need application that scale. Monolith application is a great way to start with, but over time we will eventually need to move to a distributed system. In the other hand, distributed systems such as microservices are way more complex. Distributed systems of microservices are way more complex, but it's the solution to help us scale our system. If you have a big complex system and you want to able to effectively leverage dozens or hundreds of engineers to build features in parallel, you have to move to the microservices approach. So in our journey building the system, we will eventually need to make our system more agile, scalable, and faster. And it's pretty much aligned with Conway's law, which stated that system design is largely influenced by the organizational structure of the teams that build the system. And this is one of the reasons why customers are moving to microservices, because they grow with a rapid pace. So here are a few tenets on microservices. They are polyglot, which means that you can use different programming languages and frameworks to build your services. It's black box, means that it abstracts away the complexities of each service. They are independent, so you can have multiple teams building different services. They are decentralized, and this gives you an advantage as it improves your development velocity without having to have a tight coupling or dependencies with another teams. And as they are independent service, a problem in one service will have less blast radius compared to monolithic application. Now, being decentralized and independent are two aspects that becomes the foundation of this session. Now, by having the flexibility to build services, now what we need to do is how the services could interact one to another. And when it comes to communication, we'll naturally think about APIs. And yes, APIs are the front door of microservices. They become the interface to interact with services which holds business logic of a specific domain. Right? Now, when it comes to APIs, we will naturally think to build REST APIs or any kind of form of synchronous communication. So let's imagine that we are building an e-commerce application. We have two services, order service and invoice service. Order service will take care of everything that our customer check out. And invoice service will notify the accounting, finance department, and the customer as well. So in this context, this system were built using REST APIs. When we send a POST request to order service, which order service needs to make a downstream call to invoice service, then it will be processed by invoice service before to the client. In ideal case, everything works well. But what happens if one of the service has some kind of issue? The invoice service needs to perform the request and it took longer than expected. And at the end, it will return gateway timeout. And the order service will have a problem as well because it didn't get the proper return from invoice service. Then you might think that, oh yeah, we need to build some kind of retry mechanism and circuit breaker. Those are useful patterns, but in this case, the underlying problem isn't how you handle the error, but how to minimize the error on service communication. And as a solution, we could implement asynchronous communication by leveraging message or even bus to choreograph the communication between services. Now, this is an example of request reply pattern, where client send a request to order service and all the service will immediately return a response that the request is created and return some kind of ID and the URL for the client to retrieve the result. Now in the background, since the request might take longer time to finish, the order service not directly call the invoice service and send to event bus instead. So event or messaging bus will then receive and route the matching patterns of message to specific target. In this case, is invoice service. Now, invoice service now has the request, and meanwhile, client will try to do polling request to invoice service, and once the invoice service is done processing, it will provide the result to the client. And yes, building APIs is really important, but we also need to think how services communicate effectively. And this is only one example to illustrate that we can utilize asynchronous communication. And at this point, you might think, well, asynchronous communication seems so cool, but do I need to replace all of my synchronous APIs with this? So that depends. And more than often, I see that a lot of developers successfully integrate these two forms of communication into their system and still relate to the black box concept. When we make an API call request, all we see is one endpoint URL, and we connecting through REST API. But in the background, all of relevant system that process the request interacts with asynchronous communication. And this is an example to abstract away the complexities of the system by using REST API for public API and asynchronous communication for internal services. Now, this table describes few important things to differentiate how we use API and asynchronous communication. So when we build the API, we need a central point to manage all incoming requests, and also to delegate to which resource or path this request needs to be forwarded. And not only that, we also need a safe medium because it is the meeting point between the client and the backend, which is generally exposed to the public. Now, to prevent this, API gateway is usually used. On the other hand, for asynchronous communication, for request traffic can use PubSub, queue, or even streaming. There are various implementations for asynchronous communication for different use cases. Now, for example, for microservices that have high throughput, you can use streaming. For those who require integration with several services, fan out is usually used, and you can use the PubSub or the event bus. Now, so for a summary, for the public interface, which is usually exposed, it's an SAP API that uses a synchronous communication approach, and for internal interaction, asynchronous communication is usually used. Okay, so let's dive deeper into how we could build asynchronous communication for our services. Now, most of the asynchronous communication in microservices leverage on event or messaging bus that reacts in a new event happening in the system or using a central service to connect all of services. So there are two ways on how you can do this. The first one is using choreography pattern, and second is using orchestration pattern. In choreography pattern, each service can execute independently in response to a particular event. So other services can retrieve the message asynchronously and complete their respective tasks. Now, with this architecture, services are loosely coupled and do not have a direct impact on each other. In orchestration pattern, we use a central service to coordinate all of services until the entire process is completed. The distributed character of microservices makes it challenging to orchestrate workflows when multiple microservices are involved, and developers might be tempted to add orchestration into the application. Now, orchestration patterns introduce a concept of delegating the instruction in order to reduce the tight coupling and makes it easier to replace individual service. So, in following sections, we're going to dive deeper into both choreography and orchestration pattern. Okay, so what is an idea behind event-driven architecture? Now, the idea behind event-driven architecture is to build a decoupled system that runs in response to events. And decoupled components or services within your system need to communicate, preferably using asynchronous communication. And that's why understanding asynchronous communication when building microservices is important. And an event-driven architecture use event to trigger and communicate between decoupled service, and is common in modern application built with microservices. An event is a change in state or an update, like an item being placed in a shopping cart or in an e-commerce website. Events can either carry the state such as the item purchase, or events can be identifiers like a notification that an order was shipped. Now, event-driven architecture have three key components: event producers, event routers, and event consumers. A producers publish an event to the router, which filters and pushes the event to consumers. Now, producer and consumer service are decoupled, which allows them to be scaled, updated, and deployed independently. So, if you remember the problem with synchronous API that we have discussed before, the underlying problem was how we could make sure that our architecture could support our business in long run. So in the future, we might need to add more services, and our architecture now looks like this. And you might already guess it. And this is an example on how we could move to event-driven architecture to handle the challenge that we discussed earlier. Sorry. Instead of having all the services to call each of downstream services, it's now sending an event. For example, an order was created. And we have other services to subscribe to this particular event. Maybe not all services interested on taking any action to a particular event, maybe only one or two services. But with this kind of architecture, we are giving a freedom for those services to act independently based on their task in serving requests. So that's awesome. Now we can decouple our system components and practically scale independently based on the demand. And the next question would be, what do we do with these arrows? So in this case, we need to have an event routers. Now to reiterate, in event-driven architectures, we need to have three key components: event producers, event consumers, and event routers. A producer publishes an event to the router, which filters and pushes the events to consumers. Producer services or consumer services are decoupled, which allows them to be scaled, updated, and deployed independently. And the event router will automatically filter and push events to consumers and acts as an elastic buffer that will accommodate surges in workloads, and also as a centralized location to select and filter events, audit your applications, and define policies. And by placing event router in our architecture, we get advantages. We can transfer data between systems. We can develop, scale, and deploy services independently from other teams. We can also do fan out the event without having to write custom code to push to each consumer. The router will push the event to the systems, each of which can process the event in parallel with a different purpose. And lastly, event router establishes indirection and interoperability among the system, so they can exchange messages and data while remaining agnostic. And what kind of service that we can use? Do we need to build one, or is there a better option? So let me introduce you to Amazon EventBridge. EventBridge removes the friction of writing point-to-point integration by letting you easily access changes in data that occur in both AWS and SaaS application via a highly scalable central stream of events. Now with EventBridge, you get simple programming model where event publishers are decoupled from event subscriber, allowing you to build loosely coupled, independently scaled, and highly reusable event-driven application. EventBridge is fully managed, so it handles everything from event ingestion and delivery to security, authorization, and error handling, making it easy to build scalable event-driven application. And because EventBridge is serverless, there is no infrastructure to manage, and you only pay for the events that you consume. And Amazon EventBridge is a significant addition to AWS offerings on building event-driven architecture, giving you freedom to choose the best tool in your case. Now, there are two main types of router used in event-driven architecture. They are event buses and event topics. Now, you can use Amazon EventBridge to build event buses, and you can use Amazon SNS, or simple notification service, to build event topics. And you can also integrate Amazon SNS and Amazon SQS to build a powerful pub-sub. Now, to distinguish when to use EventBridge and SNS, let me help you with this simple guidance. So Amazon EventBridge is recommended when you want to build an application that reacts to events from SaaS application, AWS services, or custom application. And Amazon SNS is recommended when you want to build an application that reacts to high throughput and low latency events. EventBridge uses a predefined schema for events that it helps you to select and filter events, while SNS topics are agnostic to the event schema. So let's take a look at how EventBridge works. It all starts with an event source. And this can be any one of any AWS services, your custom application, or SaaS application. So when you use a SaaS application integration, there's a special resource called a partner event source that provides a logical connection between the partner system and your AWS account without the need for provisioning and managing cross-account IAM roles or credentials. Now, at the core of EventBridge are event buses. Now, sorry, if you're familiar with the CloudWatch events defaults event bus, this is exactly the same thing, except you can create your own custom event buses as well as dedicated event bus to ingest partner events. Now, once that you have an event bus, you can associate rules with it. Rules allow you to match against values in the metadata and payloads of the events ingested and determine which events should get routed to which destination. So we mentioned this earlier and just want to reiterate again that by using Amazon EventBridge, we can expand event sources that's not limited only to our services, but it could also have in third-party integration. So with EventBridge, you can easily integrate your application, for example, with Zendesk, Datadog, MongoDB, SugarCRM, Auth0, Segment, and more are coming. And we love to think that with this kind of integration, it makes more easy and seamless for you to subscribe to standard third-party events that you might already use. Okay, so let's see how Amazon EventBridge in action. So in this demo, we're going to see how Amazon EventBridge can solve the systematic synchronous API design challenge by changing the architecture with leveraging EventBridge as an event router to handle the asynchronous communication between services. So this is how it looks like. So whenever order service receive request, it's going to publish an event called order created to EventBridge. Now, EventBridge will then push the event to respective services which are being the target for the particular event. Now, furthermore, few of the services will publish their own event, and so EventBridge will handle and push the event to the target services as well. Right? Now, additional event that we're going to create in this context is a fulfillment completed. And by fulfillment, and that the event by the fulfillment service, which then will be consumed by the logistics service. So the idea is to have a complete data flow whenever the system receives order creation. Now these are the Lambda functions that I use for this demo. And this Lambda function will be used in this demo to demonstrate how scalable and robust if we build microservices with asynchronous communication and event router. Now, one thing that I also like to emphasize is none of these functions know the existence of each other and no link whatsoever. All the communication will go through EventBridge as these functions publish their own events. Okay, so the first question in this context is how to publish the event to EventBridge, and this is something that you're going to do in the lab for the first lab and also the second lab. But let me show you on how it looks like. So this is a snippet code on how you can use AWS SDK, and this one is written in Python using Boto 3. So it's really straightforward. You only need to call put event API and then fill the parameters such as source, detail type, and event bus name. And the detail variable holds our payload. So your data will go there. And all of these parameters could be used when we want to define the rule in Amazon EventBridge. Now, let's see how I configure the EventBridge to handle the event. So let's go to the rule section and select the event bus. On this page, you can see that we have a few rules for each service. We have fulfillment service, invoice service, logistics service, and notification service. So let's take a look into one of these rules. Now, one of the most important components in EventBridge is event pattern. So whenever it receives an event, it will match the event with the pattern that you define before routing the event to the target. So In this context, if the detail type contains fulfillment completed, it will go to the logistics service, which is exactly what we want to do, right? So whenever the line items are fulfilled, it goes to logistics service to deliver them to the customers. So if we go to the fulfillment function, so we can see this function publish the fulfillment completed to EventBridge. There's no downstream call to logistics service, it only publishes an event. Okay. So let's change the sleep time to 30 seconds just to simulate that the fulfillment services take 30 seconds to complete one request. So the flow is started whenever we hit an API request, and the order service is our public API and integrated with Amazon API Gateway. So if we open this endpoint link, it will give us a HTTP OK status code. And let's test it out. Now this is our dashboard. Nothing too fancy over here. It's just to give us an info from our backend whenever it completes processing. So when it completes something, it's going to update this dashboard. Okay, so to make it more clear, let me repeat the flow. Whenever we make an API call to order service endpoint, the order service will publish an event to invoice service, so it could send the invoice to the customers. Now, the event that the order service has published is also be consumed by the fulfillment service. Now remember that the fulfillment service takes a bit of time that we just changed to around 30 seconds to complete a request, one single request. And once it completes the request, it's going to publish another event which is logistics started, and it will be consumed by a logistics service. And that will be indicated in this column that is shipping to the customer. Okay, cool. So let's start it. Let's start the demo. In this demo, I'm going to use artillery tools to create 100 requests. Okay. Okay, starting now, and as you can see that order service is now updating, and invoice service is being called as well, and send the invoice in this case. Okay, so now the fulfillment service is trying to complete the job, and you notice once that the fulfillment completed, it's shipping to customers. And now our requests were handled properly, right? No timeout, quite fast if I should say, and everyone is happy. Okay. Okay, so now we know how to use Amazon EventBridge. Okay, so then let's head to our lab. Here are a few guidance to help you work on the workshop. Once that you get all source code, you need to complete tasks described on each readme.md files. You are encouraged to use the provided hints, and you are expected to build the complete code, both the infrastructure using AWS CDK and the software. Now this is the main challenge because they are not in form of a complete code, right? But if you want to take a peek into the full source code, they are available in subdirectories. Now please use this opportunity to build your understanding, and if at some point you encounter any problems, technical experts are standing by to help you out. And don't forget, at the end of the workshop, please clean up all resources to avoid incurring charges, right? Okay, so next, let me guide you on how you can use the repository. Okay. So in the repository, you will find a couple of subfolders. Now these subfolders are the lab content, and inside each of the lab content, you will find two folders, source and work. Source contains all complete code, starting from CDK to provision resources and related codes to Lambda and others. And work is the directory that you need to do your activities. And for the instruction, you will find on readme.md file on each lab. So see, here's how it works. You need to read the instruction on readme.md file and do your activities in the work folder. If you are stuck with something, you can also try to get a reference in the source folder. So, so by getting the reference from the source folder, which is the complete code, you can move on or even complete your lab easily. So I hope that helps you to navigate this workshop repository. Okay, so in this lab, we're going to get ourselves with the basic on how to dispatch and consume events. We're going to use AWS Lambda function as our main computing. So here's how it looks like. So we will create two Lambda functions. The first one is to dispatch event, and that particular event will be sent to an event bus. Okay. Now we're going to use Amazon EventBridge for that. And once that Amazon EventBridge dispatch that event, it will try to send to our second Lambda function. And once it receives an event, this the second Lambda function, it will print the log into CloudWatch logs. Well, pretty simple, isn't it? Okay, so let's start this lab. You will find the instruction on the screen, and also remember to read the instruction on readme.md file in the lab 1. So I'm going to close my webcam and back online when the time is up. You will find me in the room as well, as I'm going to join our technical expert team. Good luck, everyone. I think the time is up for our lab. For those who haven't completed the lab, don't worry, you can keep continuing this at your own pace in your most convenient time. Now, moving on to the second lab. The second lab is somehow more complex compared to the previous lab, as it requires more interaction between services and also integration with Amazon DynamoDB. Okay, so let me explain how it works. So imagine that you are doing online shopping and wanted to check out your cart. So you've done your payment and everything is set. And the website needs to start the process to send the item for you. It needs to create an order, an invoice, and also send the fulfillment service to start collecting the items for you. Now, additionally, the finance team also need this particular data so it can help them to do forecasting. And in the other hand, fulfillment service needs to start the process with logistics service to help schedule the shipping for you. I hope that makes sense. Okay, so this is what we're going to do. First, we will have a public API which integrates with Lambda function called as order service. And this is to illustrate on how you can combine both synchronous and asynchronous communication with AWS. Now, this order service will create a record on Amazon DynamoDB. Okay, then from the order service, it will emit an event called order created. Now, this event will be sent to Amazon EventBridge. And Amazon EventBridge will target those Lambda functions now that will react to this particular event. Not all of them. It will send the event to the invoice service, fulfillment service, and forecasting service. Now, here's the thing. Once the fulfillment service done its process, it will emit an event called fulfillment completed, which will be picked up by logistics service. And now for every complete process on each service, we will have the status updated on Amazon DynamoDB. Okay. So that's how that you can check if the process was done properly. Now you might think that this is the lab that we're going to do is similar to the demo that I've shown you before, but with a twist. Instead of having a dashboard that doing like a WebSocket to the website, we're going to use Amazon DynamoDB as as our data store to check if the request already been completed successfully for each service. Okay, so that's what we are going to do in this workshop, and let's start the lab. Um, you'll find the instruction on the screen, and please read the instruction in the readme.md file. So I'm going to close my webcam again and back online when the time is up. Okay, so time is up and we are moving to the next segment. And at this point, you understand on how to implement choreography for your microservices. We have played around with Amazon EventBridge to help us decouple our system. Now, next topic that we are going to cover is how we could orchestrate microservices. So, in the following sections, we're going to dive deeper into orchestration pattern, and I'm inviting you to imagine that you are handling a banking system in which you need to implement an onboarding flow for creating a new account. So in this simplified banking system, we have 4 services in 4 domains. Account application service has a responsibility to accept applications for people who want to open a bank account and is responsible to return an approve or reject decision. Data checking service is responsible for performing various validations of data, such as checking the identity documentation or verifying that the home address appears to be valid. Now, the human review service, which tracks applications that needs review and allows humans to make decisions about the flag application. And finally, we have the account service, which is responsible for creating and managing a bank account after a new account application has been approved. And here's how these services work in concert with one another. The account application service takes in a new applications, performs the data checks, and then it needs to flag an application for review by a human if required, and finally passes approved decisions to the account service. And if you look at this particular use case, it seems that account applications holds a vital role on managing the workflow of account creation. Now, this is a good case for orchestration. So from the point of view of the account application service, it needs to make downstream calls to several other services and reacting to their responses. So let's quickly go through the step. When a new account application is received, it calls data checking service to check the identity information provided in the application. Right? It also verifies the address of the applicant. And then if any of those checks come back with a flag, a human reviewer will get involved to make a decision. And finally, if an approval decision was made, it calls out to the account service to open a new account. So at this point, we understand how the workflow of this account creation process. But the next question is how to translate this workflow into technical implementation for our microservices. Now, to be able to implement this workflow, let's step back a bit and quickly review a state machine. So a state machine simply describes a collection of computational steps that we want to split into discrete states. There's always only one starting state and only one state is active at the time. Now the basic building blocks of a state machine are states and transition. State is the situation based on previous inputs and causes a reaction on following inputs. Transition defines for which input a state is changed from one to another state. Now simply put, you can think of this like a workflow or an executable flow chart. Now as the steps of the state machine activate, the active state is going to get some input, do something with that input, generate some output, and indicate the next state to transition to. Now, because the nature of state machine is abstract, it's such a powerful way to coordinate workflow. And to implement a state machine with AWS, you can use a service called AWS Step Functions. This is actually my personal favorite service of AWS. Because Step Function lets you coordinate multiple AWS services into serverless workflows so you can build and update application quickly. Using step functions, you can design and run workflows that stitch together services such as AWS Lambda, AWS Forget, Amazon SageMaker, and other services into feature-rich application. You can write resilient workflows with built-in error handling and retry mechanism, and you can also audit the execution history with visual monitoring for your state machine executions, letting you visually trace and debug when needed. So let's try to coordinate the banking system workflow that we discussed earlier into a state machine. Okay, so first we'll verify the identity documents provided by the applicant. Then we'll check to make sure their home address appears to be valid. And then we might need to involve a human to review the data in the application. Then we'll wait for the review to happen. And finally, we can approve the application. So at first glance, this seems complete. But let's try to improve this workflow. Okay, so first we don't need to be doing the identity check and the address check in a serial fashion. So the result of one doesn't depend on the output of the other. So instead, we could arrange to have these steps completed in parallel. Then it looks like this. Next, we can improve the steps that happen after the two checks are performed. We should explicitly encode a step to show that human review is only required if the identity or address checks fail. So it's possible to go straight from the checks to an approved application. And finally, we should have an explicit step showing a rejected application and show that the human review step can transition to either an approve or a reject decision. And it looks like this. And here's the final state machine that we made some improvement. So there are two things that I like to emphasize. With state machine and AWS Step Functions, it allows us to create a reliable workflow. And what most important is, with step functions, we could easily adjust the flow, quickly replace and change the flow as needed. And this pretty much sums the reality where workflows often iterate to a new and improved version. Okay. So in this lab, we're going to orchestrate our microservices with help of a state machine and AWS Step Functions. And so this is the AWS Step Function dashboard. And what I'm going to do next is to quickly demonstrate on how you can test and run the execution for your state machine with a JSON file. Now, to test your step functions, all you need to do is just to start the execution and put some JSON data. You might be wondering, where does this JSON data come from? This is actually the logic that resides in your application. So you can define, you can modify as much as you need it. But this is the actual structure that I use in the applications that you are going to do in the next lab. And once that you have your JSON data, you just let it run, and you will see how it goes on your step function dashboard. Okay, so this was a quick demonstration on how that you can run your state machine with the new execution and AWS Step Function. And so let's start the third lab. So as always, you'll find the instruction on the screen and also in the readme.md file. And again, if you have any questions, please post them into the designated room and I'll be there to help you out. I'm going to close my webcam again and back online when the time is up. we understand what step function is and how versatile it is as a tool to integrate our microservices. So let's take a look into some examples on how we could use AWS Step Function. So here's one example on how we could utilize step functions to implement saga pattern. So imagine that you have an e-commerce website, and once that your customers check out their cart, we need to process the order. We start by checking the stock. If we have the stock for all items, then we can continue to process the payment. If the payments are okay, then the flow goes to logistics service to ship the order to our customers. And once that is done, we mark the transaction as a success and send success notification to customer. Now, there's a chance that there will be some issues on stock checking, payment processing, or coordinating with logistics service. And this problem usually happens especially when it comes to relying on external service. Right. So in case of a problem on logistics service, then we need to roll back the transaction and we need to cancel the logistics service and cancel payment. In case if there's an issue on payment processing, then we need to cancel the payment, but not necessarily cancel the logistics service because it's not created yet. And if there's no stock left for the items ordered, we can mark the transaction as failed and alert customer service. Now for every failed transaction, it will go to alert customer service and mark it as failed. Otherwise, we'll send a success notification to the customers. So this is a really good example on how that you could use AWS Step Functions to implement saga patterns. And at some point, I believe that you're going to need to implement saga patterns, and AWS Step Functions could help you out to maintain the data consistency for your microservices. Okay, so I think that's everything for today's session. Next, we're going to do the last lab, which is cleaning up. So some of you might still want to play around or finish the work. So I'll just give you a quick demonstration on how you could do cleanup with CDK. So first, you need to go to your root folder where your CDK app sits, and then you need to type CDK destroy, and then confirm the deletion, and then you'll just wait. Now, if everything is okay in this process, then you're good. Yeah. Now, otherwise, you might want to go to CloudFormation dashboard in case if there's any issues on cleaning up the resources with CDK, and you need to check on the stack that you have on the CloudFormation dashboard and do manual action from there. Okay, so that's a really quick and easy way to do cleaning up your resources with AWS CDK. So we hope you found this session helpful. If you like to learn more about building modern applications, visit our resource hub to get access to the newly created resources so you can innovate and scale with increased agility and lower cost on AWS today. Your modern applications development journey starts with AWS training and certification. So please visit the link if you like to build your cloud skills. And also, please do take the time to fill up the feedback form so we can better understand your requirements. Lastly, hopefully this workshop helps you to understand asynchronous communication, choreography, orchestration, and API gateway pattern that we've discussed. And before we end this session, let me congratulate you for completing the workshop. And don't forget to clean up resources once you no longer need it. As always, let me know if you have any questions. My inbox is always open on Twitter or LinkedIn. Okay, so I'm Donnie. Thank you, everyone. Keep on building and see you next time.